Now, back to tolerancing. What is a tolerance? Manufacturing a machine part to an extreme degree of precision can be difficult and expensive. Therefore, designers must calculate how much the size and location of a part's features, a hole or a slot for example, can deviate from the dimensions specified on the drawing and still perform their design function. Because generally speaking, the less perfect a feature can be and still perform its function, the less it costs to manufacture. So the converse of this is true too. The more perfect that a feature has to be in order to fulfill its function, the more it will cost to manufacture. The amount that the size or location of a feature is allowed to vary from what would be its perfect size and position is called a tolerance. In fact, the definition of a tolerance could be the total permissible variation in a dimension value, the difference between the upper and lower size limit of a feature. Now, because I'm using the term feature, maybe I should give a definition of it. A feature is a geometric element that is added to a base part, such as a slot, a surface, or a hole. So here's an example of a part. Let's say that this is the front view of the part, and we have a dimension on this part that says 1.00. So this is 1 inch from this surface to this surface. But a tolerance has been added to this, and the way it's written, it says that this is 1 inch plus or minus 0.01. Now we know that 0.01 is 1/100th of an inch, right? The designer is indicating that this height on the part right here must measure between 1.01 and 0.99 after the part is manufactured in order for the height to serve its designed purpose. The designer has calculated that as long as this part falls between 1.01 in height and 0.99 in height, it will fit into whatever it needs to fit into. We arrived at the 1.01 and the 0.99 by taking 1.00 and adding 0.01 to it, which got us to 1.01, and then also by subtracting 0.01 to it, which got us at 0.99. Anywhere between those two numbers that this part lands, and it will still pass inspection. The American Society of Mechanical Engineers publishes an industry-wide standard for dimensioning and tolerancing known as ASME Y 14.5-2009. The ASME Y 14.5 standard states the following with regard to tolerances. Each dimension shall have a tolerance, except those dimensions specifically identified as reference, maximum, minimum, or stock. Now we'll get into what reference dimensions mean and the maximum and minimum sizes, but I want to focus on that top line right there. Each dimension shall have a tolerance. That's what the ASME standard says. So if we use that as a guiding rule, whenever we make an engineering drawing and we start to dimension it, we need to pay attention to the tolerances that will apply to each dimension on the drawing. Designers control the final size and location of a part's features during the manufacturing process by specifying a tolerance for each size and location dimension on mechanical drawings. Tolerance is applied during the manufacture of the part and to the inspection of the part after manufacture. In the example below, the tolerance is shown beside the nominal dimension and is noted with a plus or minus symbol. So what's the nominal dimension? The nominal dimension is the dimension right here that says 1.00. This is for a drawing done in inches. And if we were doing that same drawing in the metric system, the nominal size would be 25.4. So we can see with our arrows and these labels, that represents the nominal size of the feature. And the feature in this case is the distance between those two surfaces. Actually, we call those two surfaces a feature of size. Now, the circles are around the tolerance, which is, in the case of inches, is 0.01 inches right here. That would be added or subtracted to the nominal size. And on our metric drawing, our tolerance is 0.1 millimeters. A definition of the nominal size is a dimension used to describe the general size of the feature. Tolerances are applied, usually added or subtracted to this dimension. In the example below, the tolerances have been labeled a little bit differently. These are called limits tolerances here. So instead of saying 1.00, 1 inch plus or minus 0.01, we actually list what the upper and lower limits of size would be for this block here. So remember, this is in inches. The metric side of that would look like 25.5 millimeters would be the widest they could manufacture the block, and 25.3 would be the narrowest this distance could be here. We call the larger number the upper limit of size, and we call the lower number the lower limit of size. Limits of size, let's get a definition for that. The maximum and minimum sizes of a feature as defined by the toleranced dimensions. All right, so let's take a look at this part, and what we'll see is that this part is dimensioned from this side over here and then has 3 dimensions. So effectively we design this slot with these 2 dimensions here. We describe that slot with these 2 dimensions, and then this third dimension gives us the overall width of our part. Now let's look at this slot down here that's dimensioned a little bit different than the slot up here. Down here we use continuous dimensions to define the edges of the slot. So a continuous dimension, we go from our baseline or our datum feature, we go over 1 inch, and then we pick up right where that ended and we put another 1 inch dimension in there. Up here we describe the left side of our slot with this dimension and the right side with this dimension. Now, what is the width of the slot in either case? Well, the slot in either case is 1.00. The width of the slot is the same whether you dimension it using baseline dimensioning, what this is called is baseline dimensioning because all of our dimensions are coming off a baseline, which we also call a datum feature, versus continuous dimensions, which we have a dimension and then another dimension. Sometimes people call this chain dimensioning. They're exactly the same though for the width of the slot until tolerances are applied. So in the next slide we're going to look at what happens when tolerances are applied to this. So when we look at the slot now, once we've applied tolerances to our 3 baseline dimensions, look at all the things that affect the width of the slot. If the left side of the slot is placed at 1.01, or if it's placed at 0.99, the slot can move from left to right by 0.01 inches. On the opposite side over here, because the tolerance of plus or minus 0.01 could be added to the 2, the right side of the slot could move over 1/100 of an inch or move to the left 1/100 of an inch. Depending on where they place the sides of this slot, that will determine how wide this slot can be. And there's quite a bit of variation because there are 2 dimensions that determine how wide the slot will be. So remember, we're using baseline dimensions here. So now let's compare that to continuous dimensions. When we do continuous dimensions, we still have a dimension of 1.00 plus or minus 0.01. So that moves this side of the slot plus or minus 1/100 of an inch. But wherever it lands, then we begin a new dimension. So the distance from this side of the slot here to this side, can never be wider than 1.01 or narrower than 0.99. Up here, because we have two dimensions affecting the slot's width could fall somewhere between 0.98 and 1.02 depending on what happens with the tolerances of these two dimensions right here. Where down here, the widest it can be is 101 and the narrowest it can be is 0.99. So you see the difference? Here's the takeaway. Designers must be aware that the method used to dimension the slot, either baseline or continuous, affects its size once tolerances are factored in. So we go backward. When you don't have tolerances, the width of the slot is the same regardless of how you dimension the part. But once you add tolerances, it's not the same. So you have to be aware of that whenever you're dimensioning a part or designing a part. Usually, tolerances on a drawing are going to be specified next to the title block in what's called a tolerance block. In the example above, any dimension that's taken to 1 decimal place of precision would have a tolerance of plus or minus 0.05. All right? And remember that if we put another 0 on that, a machinist would say our tolerance here is 50 thou instead of 0.05 5/100ths of an inch. Any dimension on this drawing that's taken to 2 decimal places of precision could have a tolerance of plus or minus 0.02 inches, 2/100ths of an inch, which a machinist might refer to as 20 thou. Any dimension on the drawing that's taken to 3 decimal places has a tolerance of plus or minus 0.010 10,000th of an inch. All right? So this is a good way to add tolerances to a drawing. So when you start to put your dimensions in, any dimension that you want the tolerance to be 0.05 for, what you would do is you would just put that dimension in at 1 decimal place, like 1.5. If you put in 1.50, this dimension or this tolerance would apply, and if you wrote 1.555, this tolerance would apply. You can control the number of places of precision in your drawing through your dimension style in your CAD program. When the number of decimal places a dimension is labeled on a drawing determines the tolerance applied during the manufacture of the part, like it does here, it's crucial that drafters label dimensions with the exact precision shown on the designer's sketch. Okay, so let's look at that. If the number of decimal places a dimension has on the drawing determines the tolerance, when the drafter makes that drawing, it's important that you follow the exact precision that was on the designer's sketch or other input. Whatever the designer gave you to draw that up with, you need to follow the precision exactly. Incorrectly labeling the precision of a dimension will change the design intent, and an error that changes design intent can lead to serious consequences in an engineering office. So serious, in fact, it could get you fired by putting a dimension down to the wrong degree of precision, and then the company manufactures a bunch of those at the wrong degree of precision. That's a serious error. Faulty design could lead to thousands of parts that do not fit or function as designed, which could require the organization to remake thousands of parts. Or they may have to do a product recall because the parts are not working the way they were designed. Faulty design intent can even endanger lives. Another method of specifying tolerances on a drawing is to add general notations in the field of the drawing. For example, these notes right here, notes unless otherwise specified, decimal dimensions to be plus or minus 0.010. So this is a general note that applies to all of your dimensions in the field of the drawing. You could also have a note that gives an angular tolerance of plus or minus 1 degree or a half a degree or whatever you wanted it to be. Okay? So if we think of in terms of angular tolerances, an angle labeled 30 degrees on the drawing with a tolerance of plus or minus 1 degree could measure between 29 and 31 degrees when the part is made and inspected and still pass the quality inspection. In the figure at right, a machine part has a chain of 3 continuous dimensions, each labeled 1.00 with a plus or minus tolerance of plus or minus 0.01. And then we have an overall width of 3 that is located inside parentheses. So we have a chain of dimensions, each 1, 1, and 1. All of them have a tolerance applied, and then we have this guy right up here that's in parentheses, but we don't see a tolerance on that. There's a reason for that. The dimension in the parentheses is a reference dimension. Now let's describe what a reference dimension is. In this example, the overall width of this part from this side to this side will be determined by the effects of this dimension here and its tolerance, plus this dimension here and its tolerance, plus this dimension here and its tolerance. So the narrowest this could ever be manufactured and pass inspection would be 0.99. The same is true here, and the same is true here. If we took 0.99 plus 0.99 plus 0.99, we might have an overall width of the part that's 2.97. However, if they manufacture it at the larger tolerance, the width here could be 1.01, 1.01, 1.01, and so the overall width could be 3.03. So the dimension we have up here differs quite a bit from 2.97 and 3.03. So we put it in parentheses and we say this is just for reference only. When you make the part, use these dimensions here and add the tolerances to them. Since this dimension is not necessary in order to make this part because the width is being determined by these 3 dimensions, we enclose it in parentheses, which means it's for reference only. If it were not shown in parentheses, a tolerance would have to apply to it, okay? And this would overdimension the part. So let's think about that. What if we had 3.00 up here plus or minus 0.01, just like these are down here, okay? Well, here's what could happen. This part, if they make the part using these 3 dimensions, might wind up being 3.03 inches wide. Well, how would you reconcile that with this dimension if it said 3.00 plus or minus 0.01? That would mean the widest this could be is 3.01, and the narrowest it could be is 2.99. Well, we can't reconcile that with that the width of this part could be as narrow as 2.97 and as wide as 3.03 if we apply these dimensions and tolerances here. So what I'm saying is this has to be a reference dimension. On the other hand, if you took one of these dimensions out and left it off, let's say you kept this dimension and this dimension, but you didn't have this dimension, you would have to have this dimension, and it would have to have a tolerance. So if this said 3.00 plus or minus 0.01, and this dimension were gone, there would not be a problem, because these 2 dimensions would only affect the width of the part and the location, of the slot, the width of the slot, and the location of the slot. This dimension up here would only affect the overall width of the slot. So if you take one of these out, you need this guy. If you have these three, this guy needs to be a reference. Now, one thing I should say is this. You could have this 3.00 with a tolerance, and you could have these two with a tolerance, and you could label this one 1.00 but not put a tolerance on it and put it in parentheses if you want, instead of deleting that dimension. A reference dimension is a dimension without a tolerance that is provided only for information purposes. It is not used for manufacture or inspection of the part. A reference dimension is enclosed in parentheses. If you remember a few minutes ago, I said that the ASME standard says that all dimensions shall have a tolerance except, and then it listed reference dimensions as one of the exceptions. So this is an explanation of the reference dimension. Now, I want to show you something here, a little bit extra information. There's a phenomenon where when you have these 3 dimensions in a row, or even 2 dimensions in a row, that when you start to add or subtract all of their tolerances, you get a greater tolerance overall than you would if you had just had one dimension that had a plus or minus tolerance on it. We call this phenomenon where you wind up with a cumulative effect on the overall length or location or size. We call that a tolerance accumulation, and that can be a bad thing. So just be aware of that you want to watch out for things like that. How are dimensions calculated for machine and mechanical drawing? Well, mechanical engineers and designers are responsible for calculating the dimensions and the materials of an object. And when I say dimensions, I also mean their tolerances. They do this by carefully considering the form, the fit, and the function of the object they are designing. And all that goes into their design. For example, the material a part is to be manufactured from, and how the object fits with other parts in assembly, and the role it plays in the overall design are all factors that may affect the overall size and location dimensions of a part. Sometimes dimensions define aesthetic rather than functional qualities. The aesthetic qualities of an object refer more to the object's appearance rather than its function. So we might say that aesthetics is involved with, is the object beautiful or not, right? Where it's less about the function. Because the designer's dimensions are carefully calculated, it's very important that they are faithfully reproduced by the drafter during the preparation of an engineering drawing. The cost of tolerancing parts. Designers must consider cost when determining the tolerances for a feature, because as I said, as tolerances become tighter, the cost of manufacturing a part may increase. One possible reason for increased cost is that as tolerance allowances become stricter, it may take longer to manufacture the part because the manufacturer will have to slow down the processes and be more careful. Another reason that cost may increase is that due to tighter tolerances, fewer parts may pass a quality control inspection. Designers walk a fine line between the desired accuracy of a part and the cost of manufacturing the part within the budget constraints of the project. So you don't want to over tolerance a part because you'll only increase the cost. So the rule is you want to give the largest possible tolerance that you can that will still allow the part to function the way it needs to function in the assembly. While tight tolerances usually add to the cost of a project, there is another type of tolerancing known as geometric dimensioning tolerancing, or GD&T, which may actually lower the cost of producing a part. GD&T is generally a topic that's discussed in more advanced machine design courses, and I recommend that if you're interested in really learning dimensioning and tolerancing, that you study geometric dimensioning and tolerancing. GDT tolerances apply to things like form, which could be the flatness of a surface, the straightness of a part, circularity and cylindricity, orientation, which could be the perpendicularity of a plane, or angularity, or the parallelism between two planes, or the position of a part's features. By using GD&T, the odds that parts will pass a quality control inspection rise, and fewer rejected parts will result in lower production cost.